Alyssa is on visualization and astronomy, but the Seamless Astronomy group over the past 5 years has been working to bring you many other things other than visualization tools. We've tried to introduce you to...
More of you will be using them after today. But let me come now to this question of big data that comes up all the time. Okay, so you've probably noticed that the popular media has caught on to the idea that there must be something to big data, and this is very trendy and snazzy. And we, of course, in astronomy have our own big data sets, and we are popular with the media sometimes for providing this big data. But I want to point out that there's another concept, and I give credit for the name of this concept to Chris Beaumont, who's sitting over there, which is wide data. Okay, where you have a diversity of different kinds of information that you'd really like to combine. And sometimes it's hard to gather that information, and often it's hard to visualize that information together. So I'm going to talk about both of these things. But let me give you an example of big data and this partnership between humans and computers that I talked about earlier. So this image in the background, some of you may recognize as the output of something called the Milky Way Project, which is a citizen science project where people are shown images, like this one, okay, here, and they have a choice of, do you see a bubble, do you see a star cluster, what do you see, okay? And so they can draw bubbles. If they see what they think is a bubble in the interstellar medium, they can use a tool and they can mark it. And in order to do that, they're using their brain. They're using their cognitive system, which I mentioned is better than a computer a priori at doing something like that. But of course, I'm talking about big data. Okay? So you don't necessarily want to rely on humans to find every bubble. And you also don't know how reliable humans are or how similar one human is to the next. So what you really want to do is leverage these things and do something called humanated computing. Okay? So what does that mean? That means that you take, for example, in this example, which again is the work of Chris Beaumont, you take the output of a project like a citizen science Zooniverse project to mark the bubbles. And so this is a set of examples, they're labeled here A, that are very good examples of these bubbles we're looking for. B is sort of okay examples, and C is terribly lame examples, okay? But all of these things were found by humans, okay, who identified them as bubbles. But what you can do is you can take those things and you can use that output as the input to a machine learning algorithm. And in this case, that algorithm is called Brute. And Chris can tell you afterwards all about the details of how it works, but importantly, it works entirely inside of a computer using input that is essentially the visual system of humans. And so what happens? Okay, well, two things happen. One is that you actually do discover some of the same things that were discovered by people, but you also discover new things, and importantly, you can quantify how sure the algorithm is that something is a bubble. So these things that say p greater than 0.9, for example, mean that they're very certain to be bubbles, and p less than 0.5 is like, oh, I'm not so sure. Okay, and the pink ones are new. But very importantly, marking bubbles in an image like this is not something that even humans can do perfectly. And over here, what you can do is you can show, this is a sample, every line there is a single bubble extracted from the data shown to experts, okay? Actual, not citizen scientists, but actual experts about the structure of the interstellar medium. And where you see a blue line all the way across, that means everyone agrees it's a bubble. If you saw a red line all the way across, everybody would agree it was not a bubble. But what you see a lot of is this kind of, I don't know, this orange category. And then in some cases, you see a lot of red and a lot of orange, like, I don't think so. But remember, every line there was identified as a bubble by the Citizen Science Project. And if you go look at this paper, you'll see that you can actually correlate how sure experts are with how sure the algorithm is, and do even better to calibrate an automatic bubble finding routine that could look at seriously large data sets. So if you see there that the human cognition is a key step in the computational process. Okay, so what about if you have big data and wide data? Okay. I'm going to come back to that in just a second, but because that's really our problem a lot of the time. But let me just show you for a brief moment what I mean by wide data. Okay. So this is just a slide that some of you have seen several times, showing an overlay of many different kinds of data from the complete survey of star-forming regions, showing you radio spectral line data as contours on top of a background image, on top of catalogs of young stars, and you have a sort of combined set of information that you'd like to intercompare. And this kind of overlays the typical visualization that you see to try to understand how these things relate to each other. But just keep in mind this particular data set when I come back to talking about glue later. Okay? But this is what I mean by wide data. And then I promised I would show you an example of a case where you have big and wide data. And I know we have plenty of theorists and simulators in the audience, so let me choose an example from simulations. These are some movies from Volker Springel, where you see many different quantities, dark matter density, shocks, etc. 6 different quantities plotted here for a simulation of the formation of a cluster of galaxies over time. Okay? So there's a lot of information in that one plot. And actually, normally in visualization, you would discourage people from using a different color table in every panel. Okay? But here, it actually helps you remember which one is which. And you can watch this over and over again and compare one thing to another. But still, you'd rather interact with it. Keep that in mind. Okay. All right, so before I go on to talking about additional tools for dealing with these challenges, I want to just remind you that astronomers tend to think of different kinds of graphs as disconnected from each other. So they don't think about often how spectra relate to images, how they relate to 3D movies, etc. Okay? So the thing you just saw was 4-dimensional in that it was a time series of volumes. Okay? But if you go backwards and just think for a minute about a 1D slice through an imaginary cube of data. Okay? In astronomy, a column through a cube of data like that is usually a spectrum, a spectral energy distribution, or maybe a time series. It's just an XY plot of something versus something else. Okay? And often it's flux versus wavelength. Okay? But then, if you think about looking at this cube in 2 dimensions, say from this front view, okay, you'd either see the face of the cube, the sum along the cube, or a slice through the cube. And those are usually portrayed as images. Okay? But in fact, right, say that this was a cube of spectrally resolved images, right, then any line through there is still a spectrum. And so sometimes you have the case, right, where you actually have all 3 dimensions. You have a volume, say, of spectral line data, for example, right? And then your choices for showing that are like 3D renderings or 2D movies, some of which I'll show you in just a moment. And then if you have 4D data, okay, you do the kind of thing I just showed you a minute ago from Volker Springel's data where you show movies changing in time. Okay, so now let's look at some wide data that is one of these 3D cubes. Okay? So I showed you that, I told you that we would come back to this image. And the way that you see it here, the green contours are showing you the sum of emission in the carbon monoxide molecule along the line of sight. Okay? But that's hiding information about where along the line of sight that carbon monoxide emission comes from. And we actually have that information, or at least we have information about the velocity along the line of sight. And so remember I said that 3D data, you could show it as a 2D movie. So if I slide this here, okay, this is just a movie, and that white fluff is showing you slices through the cube, channel maps, okay? And the white fluff adds up to the green contours, okay? So those 2D slices add up to the full volume. But I would argue that it's extremely hard to see what's going on other than that there's some sort of overall velocity gradient in this thing. But it's hard for your brain to put that back together into a 3-dimensional picture. So several years ago now, we partnered with some people in the medical imaging world, and we did this project where we started experimenting using medical imaging tools on data like this. So here, you see the same data, but now you can holistically see how all the information fits together, and you can see arcs, and you can see spikes and outflows, and what you'd really like is to be able to put those stars back in there in 3D, if only we knew their distances or their velocities. But anyway, you certainly can understand the pattern of the gas emission much better from something like this. Now, I'm guessing that some of you are saying, well, that's nice, but you're not going to stand there while somebody's reading your paper and move the mouse around and slide the data around and explain this to them. And that's true, okay? So there's this very important question of what do we publish? Now, let me just step back for a second and give you some perspective on what we've done in the past, okay? So you're probably familiar with Sidereus Nuncius, which I mentioned at the beginning. So that was published in 1610. It was published as a book, a monograph by Galileo. It had these diagrams that I showed you on the early slide. And very interestingly, the diagrams were integrated with the text. You notice it doesn't say figure 1, figure 2, etc. Try this in the AppJ right now. Even that would be difficult. Okay. Anyway, then 1665 comes along, and the first scholarly article is published in the Philosophical Transactions of the Royal Society. Okay? If I blew that up for you and told you it was a page from the AppJ and turned it to be not yellow, you would believe me. Okay, so not much has changed since 1665. 1895, the spectroscopists broke off from the astronomers and they started the Astrophysical Journal. Okay, so it's been since 1895 that we've had that journal. And it looks pretty much the same as 1665. So no wonder you would ask, well, what do you do with that kind of 3D medical imaging result that I showed you earlier? So some of you know that in 2009, we did do something with that. And in fact, what we did was we published it in Nature as the first interactive 3D PDF. And so what do I mean by that? This is a little section of that same molecular cloud that I showed you before. And the paper, which is not important for today's topic, is about self-gravity and star formation. What's important for today is for me to show you what happens in that paper. So here you go. You look at the front page of the paper, it looks like just a totally normal paper. You start scrolling through the paper, and you notice that on the second page there's this funky button that says, click to rotate. And you say, okay, let me zoom in and see what goes on. Let me click that, click the figure, yeah, And then if I start playing with the figure, and I click and drag, you notice I can actually move the figure directly inside of the PDF. And not only that, I can look at various pre-made views, turn off structure that isn't self-gravitating. I can notice that those pieces are disconnected from each other. I can look at the other silly structural decomposition of the data and notice how silly it is compared to the much better one that we published on the left. Okay? And then I can wish, actually, that those graphs below that actually describe the same data were somehow connected to the graphs above. But I'm not going to show you that in this video because, in fact, we didn't do that in 2009. But I'll show you later how you connect those kind of statistical graphics below to the more literal representations above. What I want to tell you now, though, is going to foreshadow this great story that I hope I'm going to tell you at the end of the talk about how little tricks like that, like publishing a 3D PDF, can get people's attention and move the whole community forward. Okay? And that's what we're hoping to do, actually, in most of the seamless astronomy efforts. So in this particular instance, what happened is Josh Peak over there, who's now a Hubble Fellow at Columbia, saw this trick, shall we say, of the 3D PDF in Nature. And he said, that's great, but you know, they had this $1,000 software from Adobe to be able to do that. And by the way, the reader, the free reader, can manipulate the graph when you're done. You only need money to make it in the first place. But he said, I don't want anybody to have money. Let me see if I can find an open source way to make a 3D PDF. And in fact, he did. And because, how many people know about AstroBetter? Raise your hand. That's good. Okay, that was half the audience for those of you on the webcast who can't see. Okay, it should be 100%. Okay, if you don't know what AstroBetter is, it's a wonderful blog that has all kinds of tips and tricks like this, as well as interesting discussions about the astronomy community. Anyway, so Josh comes up to me at the AAS that year in 2012, and he says, Alyssa, I'm so excited. Here, look, I made a free 3D PDF, and I'm going to write it up for AstroBetter, and here it is. And since then, several people have been able to use free tools to make a 3D PDF. So there's the actual foreshadowing where I'm going to tell you an amazing sequel to that story, okay, that also involves Josh Peak in a few minutes. Okay? And I'm going to explain what all those other icons are and how these tools fit together. But before I do that, I want to go back to this publishing story and the world that we live in today. So a lot of data are locked up in journals. Okay, so in other words, you read a journal article and you say, wow, that's a nice image, or that's a nice spectrum, or I wonder how that compares to my data, but you basically just have some sort of PDF image if you're lucky. And over there is Alberto Akamatsu, who's instrumental to the story I'm about to tell you, which is about ADS. He's nodding. Yes, we lock up this data in our journals. What should we do about it? Okay, here's what we should do about it. You should appreciate that many images come from journals, and so here's that background image that you saw in the complete example. That's an ancient image from Barnard from the very early 20th century that you can see in this online catalog of Barnard's images that you can find on the web. You can also find it in an article in the Astrophysical Journal, which is stored in ADS. Now, some of you know this trick, but I'm betting not all of you. Did you know that you can move that image to flicker and then see where it goes on the sky? How many people knew you can do that? Those of you who've heard about this before, but not many. Okay, so watch. So you move that image to flicker in this particular case. You put it in a group called Astrometry on Flickr. Then there's this wonderful program from our collaborator David Hogg and friends, called, including Doug Finkbeiner if he's here, called Astrometry.net, which is let's just call it a magical, wonderful computer program for the moment that identifies stars in the image, compares them to a catalog, figures out uniquely where that image goes in the sky. Okay? So that runs in the background on Flickr. Put some comments on Flickr. You can click on one of those comments that says open in Worldwide Telescope, and then that image will open in a web page showing you whatever imagery you want in the background, because Worldwide Telescope can change the imagery in the background. So let's say I wanted to put that image over a WISE image. It would look like that. Okay, so what is the ADS All-Sky Survey? Part of the ADS All-Sky Survey is an effort which is now quite underway, and a lot of it works, to suck all of the images out of all of the journals in the ADS and put them through this kind of pipeline and let you see them on the sky. And we can share with you the early results from that effort of putting the images where they go. But there are two other parts to the ADS All-Sky Survey, one of which is finished, and this one is just beginning. So I'll get to the finished one in a second. But the other one is really fun. So I mentioned the Zooniverse earlier, which is this suite of amazing citizen science projects. So we have a new collaboration with them where what we're going to do is for the images that don't have stars in them. You can't use this magical astrometry program, but humans can read off the coordinates and the captions, and if you have enough volunteers, you can actually collect the information of where these images should go on the sky, regardless of the fact that they have no stars in them. Okay, so they could be some, peak intensity of CO emission, like this image here on the right. So this project is called Old Astronomy, and what will happen is these images will go out and be served to people who are willing to help, and the entire corpus of images in the Astrophysical Journal and all the other journals in ADS, you'll just click on them in ADS and you can put your image back on the sky, or you can suck it out with coordinates and compare it to your modern data or to other data. Okay, so I said that there were three parts of the ADS All-Sky Survey. So the first part is this so-called astro-referenced images done automatically through astrometry.net. And then the second part is this old astronomy effort. And then the third part, which is now working and you can go try, will actually give you heat maps of where the sky has been studied for what reason. Okay? So in other words, this image here, and that's what you were seeing in the slideshow in the beginning, is not any image of the sky. It's an image of articles on the sky. Okay? And you can actually filter the articles by various subjects. And two people in the audience who deserve tremendous credit for this are Gus Mensch and Chris Beaumont, who helped make the viewers and collect all the data, and many thanks to the ADS team as well as our friends at Worldwide Telescope and Aladdin. So you can see the results. You can see these heat maps in both Aladdin and Worldwide Telescope, and in the future you'll actually also be able to extract them and do whatever you want with them. But right now you can go to adsass.org and actually see why the sky was studied, for what reason. Okay, so that's how we can take the past and suck it into the present. Okay, what I want to show you next is how we can actually go to the future. Okay, so this is the so-called riveting sequel. All right, what happened? What happened was our same troublemaking friends, okay, including Josh Peak here, who I hope is watching, okay, attended this meeting called Dot Astronomy. So Dot Astronomy 5 was here in September, and some of you